तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking at simplified tool so far, and we started with the following commands. We started the simplify window by opening a icon here called Simplify Pro by double clicking that, and then we once the window was open, we saw that how to open a new file, and click on file new to open a new project. A new window opens, click on project file, type combination circuits. This is the design file that we had typed, and in file name field, and also type the desired file location where you wish the new project to reside. This is the place where your V files are residing, and then you assert OK, and then the project window opens. This is what we have already seen here. This was the main window that we had. So main window looks like this with different options available: open project, then add file, and once again you have a file, edit, view, project, and so on. And P is also for project, you can open the project from that also. And so this is the window that we had already seen here. That is what we have seen just now. And a new project was also created by this window. So we used this project file and then gave the combination circuits, identifying the design file, and then the entire path is shown here, and finally we said OK, and the new project was opened. And once we had opened the project, we had to identify the actual vendor, then device, then package. That means desiring a particular number of pins and type of package and all that, and this is what it is. Click on new implementation, options for implementation window opens. In that window, click on device, select Xilinx Vertex in technology field. XCV800 is the one of the devices that we had selected then in part field. Then -4 stands for the speed, and there are other versions -5, 6, and so on, and they are higher the number, higher the speed that you can get in Xilinx. In Altera, I think the reverse that is true, and you can change to any other vendor device accordingly as per your needs, and this also we have seen earlier. And once you are done with this, just say click OK, and it is up to that we had covered earlier. Now we will carry on from that. So what we need to do is, we have design, and your design may consist of several files, and a hierarchical it may be, and as per the flowchart that we had seen earlier, and wherein we have seen top down approach and bottom up approach, and going in through several hierarchical files. And if you have several such files, you have to add all these files, and in this case of combination circuits or sequential circuits that we are going to see, will have only one file for the design, and so you need to just add one file. So how do you do that? Click on add file menu on the left. This is the file that you have here for add files. So this is the window that opens when you say, when you click on add here, you have an add file here. If you click on this, window opens. In this you have quite a choice to choose from. I mean, you can move by clicking this, or clicking this you can go up the folder, folder by folder you can go up, and if you click here you can go down if you wish, and you can just by clicking at appropriate points you would land up in the decide folder wherein all your design files are residing. So for example, we had used combination circuits, that is also here and highlighted here, and there are other designs as well, and one such is sequential circuits, and there is also a test bench, but you should not use test bench in synthesis. This we will see little later on. So as far as this window is concerned, so once you have selected the design file, one after another you will have to click. So first, since this design has only one file, we just click on this here, and the same name will be replicated here, and it just says whether your file is a .v file or .vht. .vht stands for the VHDL, another HDL we have already seen, and you can whether it is .v or .vht, it is all same here. So this .v or .vht will discriminate what they are, and the entire path is also mentioned here, and you can see that it is VLSI design verilog in the last folder, and in which this design file is located. And once you in fact this does not appear right now, what appears is only this, and after this you have to add this file into the synthesis that you need to do. So what you do is just click on add. Upon clicking you get this here. So that means to say this particular design is included in your list of files, and like this you can go on listing as many number of files there are in your design. And once you have done this, just say if you want, suppose by mistake you clicked on the wrong design and file, so you can go highlight them by clicking on that and then say remove. Suppose you have made almost, all of them are incorrect, then you just say remove all. So it will remove all the thing, and once again you can add. And another approach is you can click on using control, and you can, or shift, so and you can select more than one design files, and then finally say add all. And normally what you have to do is you have to follow some hierarchy here also in the design files. So you start with the lowest level and then go up gradually one after another. So that is the way it should be done. So it's preferable that you add these files one after another by using just add. Click one file, then just say add. In this fashion you can keep adding more. And right now this particular design has only one file, so we don't have need all the details that we have already seen, yet for the sake of completion I have given that. And again, coming back to the summary that we have had, it just summarizes what we have just now seen. Click on add file menu on the left, select files to add to project, window opens, click on the design, say combination circuits listed in the window, also click on add button on the right to include the design file, and the selected file is displayed, click OK. This is what we have seen. In this manner, add all the files in your design. While adding files, add starting from the lowest level of files going up to the top design file. This is what we have already discussed. And we have also said you should not use a test bench in this, because test bench is meant only to test your design and it is not part of the design. So, there is no meaning in synthesizing the test bench. So, many beginners do the same mistake of including the test bench and then land up in trouble. It may give lots of errors or warnings, and therefore, be on the caution. So, that is why here it is said never use the test bench for synthesis, only your design is valid. Alternately, make sure that all the submodules of your design are included in the top design. So, this also we have already seen. I mean submodule in sense the hierarchical files that you had just now seen. So, next step is let us go to the actual Synplify window. So, this is the window that we have which is already open, and we have seen that we have to open one of these revisions also. So, let us say we have this already open. So, let us next step is we have to mention what frequency we want to synthesize. That is to say, your combination circuits, which is a hardware design, at what frequency it should function. So, this is only a desire that you are going to express. Say if I say 100 here, it means your desire of executing your codes at 100 megahertz. Mind you, this is only a simulated situation, but in synthesis what you are going to get is analysis of your design to find out whether find out the suitability for this frequency that you have chosen, and often that you may choose a high value and what the synthesis may report may be much lower. That is to say, because of the internal gate delays etc., it may not be in a position to offer you this much high frequency of operation. So, you may have to tone it down to what it reports, and mind you, even this is not final, only in place and route you get the actual frequency of operation. This is only a rough estimate, we should say, and in some cases if you have this FSM compiler resource which is ticked, you may land up, you may get some peculiar warnings or errors. So, in that case you can just switch off this by removing that, clicking on that. And so, what we have seen at this step is we have just added in the menu the frequency that we want. So, that is what the step 5 says. Set the desired operating frequency using the frequency, that is megahertz, it is reporting menu on the left. So, next step is now you are ready for running the synthesis. So, this is done by this button. So, I will just read this once again. Click on the run button on the top of the window to start the synthesis. So, compiling followed by the mapping of your design will be displayed on the window. See, first once you say run, it takes your combination circuits.v which is the design file, and runs the compiler actually. So, in order to find whether there are errors etc., and if there are errors it will report, and once this is successful it will automatically go on to the next step called mapping. In mapping you have already selected the device earlier in the few steps earlier, and as per the mapping that you have done, and it will actually take the primitive cells available in that particular FPGA. We will go into the cover more details as to what these cells are, and that is what is meant by mapping. And so, after compiling is over, mapping will be started, and once this is also over, it will report that synthesis is done. So here followed by the mapping of your design will be displayed on the window. The completion of synthesis will be indicated by a done display, and fix errors if any and repeat 6. So this step is 6. So you have to keep on going around until you are free of all errors, and take care to heed the warning messages that the synthesis tool gives. We will go into the details of this later on, and also look at the warning messages and do the needful. That is what it means. So you need to note one of this, and before we go for this, let us see where we are in the this is the Synplify window. This is the live window, and we have already mentioned 100 megahertz. It is written as megahertz here, and you can see one of these windows hopefully. So you can see the zoomed version. So frequency megahertz. So what you can do is, if you want to change this one 1 megahertz after another, you just need to just click this up arrow. It will if you click once, it will go to 101, and every time it advances by 1, and similarly it will advance down by 1 if you click this arrow. And this what we are saying, the tick marks here it will be safer to remove. We do not really need these features for the time being, at least. So coming to the Synplify window, and what we need to do is, we need to run the file. So that is what we have seen in step 6, and let us run. This is revision to combination circuits. Let us run this. So what it says is, no HDL files to compile in project combination circuits. So what we have not done is, we have not added the design file. So what we need to do is just say add file. So if you say add files, it lists all the design files here, and we need to add the design file combination circuits. So you can either double click or single click and then say add. So as I mentioned earlier, the same selected file along with the entire path is displayed here, and once this is done, say OK. So we have added in this combination circuits design file, and now let us see whether it does the job. Now you can see that it was doing the compiling, that was successful, so it went on to the mapping. So that is what is happening in the window there. So once it is done, it reports done, and if there are warnings, it would have given warnings. That means it is error free. And how do you see look into all the details? So you have what is called a log file. If you click on this, a log file will be opened, and we will go back to the command summary and let us see where we were. So that is what we have done here. So click on the run button on the top of the window to start the synthesis. Compiling followed by the mapping of your design will be displayed on the window. The completion of synthesis will be indicated by a done display, and fix errors if any and repeat 6. Also look at the warning messages and do the needful. So we have given a note here. Let us see what it says. Tick right map Verilog netlist in implementation. Before we come to this step, we will go into the log file as such. So here you see a view log, and if you want you can. So this is the zoomed version. You have a button for view log. If you press on this view log, this log file will open. So before that, what we need is, since it will be very tedious for you to have a look into this log file because font size is not enough. So we will open one we will open one WordPad so that we can just copy the log file from there and then copy it here with a bigger font. Let us say we want some 24 font. So, we will just and perhaps a bold, then we can see with ease. So, now what we need to do is we will go back to the Synplify window and then we will just click on view log. So, it opens a log file here, and as I said this will be difficult for you to read. So, what we will do is we will just copy some of this and paste it here in WordPad so that you can view it more clearly. So, the starting of compilation is reported here, what time and so on is reported, and this is from Simplicity Corporation. So, all that and then so the entire path where your design file is located is also reported here, and I is for information. Look for this symbol at, so they throw some light as to what it wants to communicate to you. So, and here it reports Verilog syntax check is successful, and your top module was combination circuits, and it was synthesizing these combination circuits, all are reported here, and how much time it took for processing, all are reported here. And since we had selected Xilinx vendor, it is reporting that as well, because mapper means it is mapping onto the actual FPGA device. So, since it is vendor specific, that which vendor it is reported here, and you can see other things you can easily conveniently go through. And here it reports, as I mentioned, there are primitive cells in the FPGA such as input buffer, output buffer, and even within output buffer there are high speed buffers available. So, if the timing constraint that you had mentioned is not met, so what it does is it automatically maps onto a buffer which gives a better response. I mean your frequency of operation improves by changing over from one of these buffers, let us say one output buffer to output buffer with this extension. So, that is what it means here by this statement. To improve timing, this has been changed. This is automatically done by the synthesis tool, because it is part of the synthesis tool to do so. And once again it is all same, so I do not have to repeat. It is repeating for different signals that you have in your design. So, if you just remember more match, we had in one of the examples there, and all of them are primarily the same. And now you see the one N stands for note, and there may not be much of a difference between information and note, right. It does not really matter what they have nomenclatured, you just look into what it reports, and it is quite easy to follow. And once again it says output buffer is reconfigured to another, and so now that we do not need this portion, we will remove this, and we will look into the other aspects of the report file. So, all of these are primarily the same. So, I will just bypass those and then tell what is relevant or important to you for analysis. So, it's this will throw light into the working of your own design, and in essence you can analyze by using this report file. And what it says here is automatic conversion of slower pads to faster pads. You can even have the option of turning off this conversion from overbuff to the higher speed thing, and it is normally preferable to just leave it as it is, because we are everyone is anxious to have extra mileage, or rather timing closure. So, that is to say highest possible frequency of operation we may be aiming for most of the projects. So, we can as well agree with what synthesis tool is doing. And the option to pack flops is a flip flops in the IOB has not been specified. So, there is also a provision for specifying this. As a default we do not specify. So, it may not be that important, probably later on you can experiment what they are. And finally, it says writing analyzed database, this is the path, and the extension file is for this. So, the data that is being analyzed is saved in this file, that is what it means. Then it also has one important file called edif, and this is very essential if you want to migrate from this to the synthesis to the place and route, which is the next tool that we need to have. So, this will be a .edf file, and EDIF means electronic data information format. So, this comes as a standard format, and normally the third party vendors would be writing in this format, in this standard rather, and that will be taken as input by the vendor specific platform for place and route. And so, this is an important thing which we can generate. We will be having a look as to how to do that. And now what it says is, okay, I will just copy this portion here up to this. So, N is for note. Automatic conversion of slower pads to faster pads can be turned off using attribute. So, by giving this attribute it can be turned off, that is what we have already seen. The option to pack flops in the IOB has not been specified, that also. Then you have seen all this, and writing edif netlist and constraint files. Constraint in sense the frequency that you had asked for is basically a constraint, and associated timings are also available, right. You can it creates these files as well. So, then what you have is the starting of the timing report. So, now we have already seen that one more I want to show you. It is already here. So, these are all the combination circuits we have seen earlier, and before we can also see view the schematic etc. When we come to that, we will have a comparison of that. So, let us see what the timing report says. So, top view is again given here, and a number of paths. I mean, it goes through a labyrinth of gates. So, those paths are also specified, and if you do not specify, a default will be put. In fact, 5 is the default that has been put here, and this timing report estimates place and route data. So, even here it makes so to say a place and route, and the actual place and route however happens only in the next tool such as Xilinx place and route, and so it says please look at the place and route timing report for final timing. So, in fact it is the vendor specific thing that you will have to look into, and then clock constraints we have already seen, and cover all flip flop to flip flop, flip flop to output, input to flip flop, all this timing. Even synthesis tool will report all this. So, we will go into the details later on, and input to output paths associated with a particular clock, all this will be reported. These are all very essential if you want to really make a serious design as such, because if you want better performance in terms of frequency operation, so you need to know how much delay it has taken for a particular path, and it may so happen that only some paths are very critical, and they are the ones which are really slowing down your operation. So, having look into that, insight into that, so you can see how to redesign so as to improve the timing, and in future we will see how to improve the performance. And right now what we will see now is the actual frequency that we had asked for is 100 megahertz. So unfortunately it is all folded back, so you may have little difficulty in seeing this clearly. I will explain what it is. So it says clock frequency. Clock frequency, what you have asked for is 100 megahertz, and what it is able to give is 90.9 megahertz, right. And what was the device actually? So that also will be listed later on here. So we will go to a Synplify window. If you see towards the end, it is XCV 600 EHQ 240-8. This is the device that has been chosen, and so looking at this window, these are all clearly laid out. This 100 megahertz is requested frequency, and estimated frequency is 90.9 megahertz. So it is all completely in disarray, but this is the best we can do, otherwise I will have to arrange it, which will take, it is a time consuming thing. So we see that requested frequency is 100 megahertz, and then estimated frequency is 90.9 megahertz. This we can see here in zoomed version, and it is slightly in disarray, but you can make it out. Requested frequency is 100 megahertz, then estimated frequency is this, and then as I mentioned, it is easy to divide 1000 by 100 megahertz in order to get straight away in nanosecond. So what you get is 10. So that 10 nanosecond is what is appearing here, because frequency and period are inverse. It's straight away in nanosecond here, and so next one is this is what you have requested, because you said 100 megahertz earlier in the frequency, that is in this window. So if you see this, this is the window. So because you had asked for 100 megahertz, it was like that. But it could meet only 90.9 megahertz because of the gate delays and so on. So and again, design to design, this will be varying, and even the same design you can improvise on this timing if you have a fresh look into the entire paths, etc., which we will be seeing later on, and thereby you can even improve either marginally or even better. Yeah, if I have a question.
Can I improve it using a different chip?
Please repeat your question.
Can I improve that frequency using a different chip, higher speed chip or something?
But like you don't call it as an improvement, it is a totally a different mapping as such, right. So whatever, why do you go for a particular chip? Because you have the hardware available with you, right. You must have conducted a complete survey earlier, and then in to a particular vendor and particular device based upon your actual requirement, right. It may might have been dictated by users themselves. So you don't probably have much choice, and swapping from one to another, it may not be meaningful. To just because you just want different timing, you cannot keep on changing device, right. Device will have to be frozen unless it is merely for learning sake. It has no meaning, right, because your target is what you have to decide. I am not saying that right at the design stage you have to decide this. You have plenty of time to decide, but the point is, I have mentioned earlier, there will be a team of engineers working for the mechanical design, then the hardware design, that is making the PCB, then layout and so on, and so also the so called software team who will be working on Verilog, and all these teams will have to be coordinated, synchronized, and unless you had frozen the design, that also I had covered earlier, unless you freeze those specification, you cannot go forward, right. So it is important that right at the beginning stage you have to make a decision, and unless something goes thoroughly wrong, you can't afford to change the device from time to time. So, you may have to freeze at some point of time. So, now that we have gone this far, so this implies that we have already frozen on a particular device, and therefore, we will have to stick on. So, what we can do, the flexibility that you have here in the same category is the package is what is going to count. So, you can change it to another type within the same vendor and retaining the same type of package. For example, HQ240 you can stick on to that, and even within this you have 3 or 4 speed ranges. So, you can always select from that, right. Okay. So, what we see is corresponding to a 90.9 megahertz operation which it has reported, and even this is not the final thing. What will be reported by the place and route tool only will be the final thing, right, that we will see later on, and this particular frequency might come down in that I mean say Xilinx tool, for example, for place and route, or it may even go up. We can't exactly say how it will behave. It all depends upon the complexity. From my experience, I can say large designs normally tend to get slows down in place and route, whereas small files which will not be the actual design, final design, will tend to go up. So, this is not a clear indication as to this will be the final frequency. What will be reported by the Xilinx say place and route only will be final as far as the Xilinx FPGA is concerned, and corresponding to this the time period is 11 nanosecond here. So, you note the difference here, and this is referred to as slack time, and it is a minus slack time. So, be on the guard if you see a minus here, it only shows that it has not met the constraints that you have asked for. You had asked for 100 megahertz, whereas what it has to offer is only this. So, this is the price that you had to pay, and at times you may have to pay a much more dearer price than this, and the difference we have already seen is this slack time here. All of them are in nanoseconds. And then coming back to the window, let us progress further. We have seen that there are paths, multiple paths, and this hereafter what we are going to see is precisely these paths. So, here I will just copy once again here. So, what you see here is this is a report for input ports, all input ports in the particular design. You remember that we had used ABC as input, then I0 for mux and so on, right. If you remember, if you do not remember, you can just recollect from here. So, AB are all inputs and these are all the outputs, then we had gone for mux. All I0, I1, you can see this is a 4 input mux, then 8 input mux and so on. So, when we see this, that is precisely what is reported here, input ports first, then followed by output ports, and all the signals will be reported, and we will see one after another all this. So, first thing what we are looking at is these inputs, and you can see here what does it say. So, where is the starting point? What we are going to see is what is the path it travels, a particular signal, how it goes, and at every point of time how much delay is caused by the cells or gates or whatever the what they call is cell in FPGAs. So, we will go into the details, and to start with, this is for ABC, all these are inputs here, and now so these are all mentioned as 0 because that is the start for this, and how much time it takes to come out of the input buffer. This is not clear from this, I think it is input buffer, but we will confirm it later on. So, what is important is it gives the time here, actual delay it has taken place. Naturally it might mean some either the net or some buffers, and these are all in nanosecond. And so you see here slack time is also reported. Slack is what we have already seen. So you have asked for one thing and what has been achieved is another. So the difference is what is called slack, and the two columns you would notice to be same. So it merely lists all the inputs here, and some of them are negative. So let us find out why they are, and right now details are not enough here, and to find out what it means, whether it is a net delay or the gate delay. And for all the signals it is reporting here. And next is so similarly outputs are also listed in this fashion. Some you can see. So you can see the outputs listed here, and the arrival time, that means data delay is what is mentioned here, and we had asked for this is the output. So it has taken it has started at a particular reference point. Starting reference point is given here with reference to a clock, right. Of course this combination circuits has no meaning with reference to the clock as such, but since no reference was there, it has taken this as reference by default. So what it takes is the D naught manifests only after this much time. So whereas you have requested 10 nanosecond, so the difference is slack. Note that they are all positive slacks here. That means you have still cushion in this. So you can jack up your frequency of operation as far as these outputs are concerned. So from this like this, if you analyze each and every output, you will know where negative slack happens. So they are the points that where they are the critical paths that you will have to reconstruct designing. So you can see these are all the inputs we have already seen. Similarly, there are so many other outputs F5, F9 and so on, and all of them report more or less same. So around 6.379 is the arrival time, whereas 10 nanoseconds you had asked for. So lots of cushioning here, 3 to 4 or 5 nanosecond available. That means as far as these outputs are concerned, you can speed up the operation, you have lots of scope there, and some of them it says timings are not available. We may have to look into namely F11 to F12, why it is not available we will have to see, and let us skip those, and you can see a negative time somewhere. Oh, okay, it's here. So if you see here less, you can see here so you can see negative timings for a less match. So these are all critical paths, right, and it's only losing very marginally. So you can have a look at this and see whether you can improve the timing. So if you can't improve the timing after doing your best, probably you had to tone down your frequency operation, or you may have to go for a higher speed version. So, similarly it reports for some carry mux 2, mux 4, mux and sum total and so on, and all of them are safe. I think this less and match are the ones, and the worst is I think it is -1 nanosecond for match. So, if you have a look, then you can into the schematic which you can view, and then you can analyze further, and let us see what more the report file says. So, again some more negative results are reported here. For number, we had done sum and comparison of two numbers. So, in that example it is showing this here. And once again same match etc. reported here. And let us have look at this. So, here it says for path number 1 whatever, so it is mere a number here to keep track of how many paths, and the required time is 10 nanoseconds, and slack it is mentioning here. The total propagation time for this signal, this is signal, which signal let us see. If it says here the starting point is for number 1, and it is a 8 bit, and ending point is match here, right. And even with this actually the problem that was encountered is not for all the bits, but only for a bit 0 bit here, and this is the start and this is the end match. So, number 1 it is only finding a match between two numbers, that is what we have already seen here. These are all the two numbers. So, when a match is this one? No. So, these are all the two numbers, and if a match is found, that is after addition, if the sum is equal to the preset value, then a match is reported. Otherwise, if it is greater, more, and if it is less, then less goes high. So, that is the actual circuit that we had coded, and for which we saw, and the synthesis report is here for that particular thing. So, what we had is number 1 and 0 bit, it has 7 through 0 8 bits totally. So, the problem that is associated, I mean the path which is critical, so is for 0 bit. Here what it says is it starts, I mean goes through the labyrinth of different gates and primitive cells, and it reports the delay at every point of time. Once again it is in slight disarray. So, what I will have a look in this and tell you. So, this is number 1 and 0 bit in question. So, that is a net. So, type means it is a net. So, type is net here, this is the 0 bit in question, and then what you have is, so next one is pin number it reports, whether that particular thing is an input or output, or if it is a net, neither of this. So, that is what is implied here. So, number 1 0 is reported there. So, number 1 0, and whether it is input port or output port will be reported here, but in this case it is an input net, it is basically a wire. So, it is just a physical wire there, therefore, it is neither an input nor an output here, and So, the next one is so the direction, pin direction is in or out, it echoes the same thing. And next one is an important thing which says the delay associated with this. For example, this number 1 is reference time is it is all relative and it is 0 here, and then progressively delay at every point of time. For example, next one if you take, it goes through an input buffer and that is an input. So, it travels via the net, and here it reports no delay there, net delay it has not reported here, say actually this is the one. So, this is for the net input of the buffer. So, it goes this number 1 0 bit goes into an input buffer, and the net delay is 0 for there, and output of the buffer is what is reported here, and it takes 1.948 nanoseconds propagation delay for this particular input buffer. That is what it means by delay. So, at every point of time it goes through another for example, let us say it goes through a lookup table, 2 input lookup table. As I mentioned, FPGA has different primitive cells, and they are all input buffer, output buffers, LUT 2 input, 3 input, 4 input, and then mux, 2 input mux, and so on. And these are all the basic components an FPGA is composed of, and most of the FPGAs are like that, and vendor to vendor and within the type it may change a little. And so, what you see here is the number 1 will finally manifest as some output such as match, but it will have to go through a number of gates such as I buff, then LUT 2, then mux, and so on, and at every gate or cell what you call, there will be a delay associated with that, and that is what is reported here. And finally, what it reports here is the cumulative delay. For example, this is the time, arrival time. So, if you started with 0, then first gate contributed to 1.9, and so is the case with the cumulative delay. So, the next one, that is LUT 2 contributed to 1 nanosecond. So, this is cumulative, this and this gets added up, and so on it goes to finally reach the match, and when it does, it has taken 11 nanoseconds. So, in this fashion you can analyze any of the circuit of your design, and then make a decision as to whether you can rewrite your code so that you can improve the speed. So, we will continue with this in the next class. Thank you.